Camelia flying faster. We've been talking about how slow things are, and well, I supposed to talk about how slow things were and how much faster they are now. So, actually, we're talking about Rakudo Perl 6 on MoarVM. This is, of course, the most advanced Perl 6 implementation that we have. And we have, since Christmas, we have had over 8,800 commits, which is basically about 1,000 for MoarVM, about 1,300 for AQP, about 3,300 for Rakudo, and for documentation, also about 3,200. So that's about 22 every day, single day since Christmas. I think that's quite a lot of work. So it's almost one every hour. We're working for the hour, but so get more people in for 6 involved, and by documentation, if you find a problem with documentation, it's a good way to start. So Rakudo Perl 6 basically depends on a number of building blocks. And the biggest one actually, or the one at the bottom at the moment, is basically MoarVM. It's short for meta model on a runtime, or as it originally was called also the mother of all runtimes. But it's a dedicated virtual machine for running Perl 6. So, although apparently the original virtual machine for Perl 6 was more intended to be a generic virtual machine, MoarVM is dedicated to Perl 6. Having said that, Perl 6 is just a language implemented using MoarVM and AQP. So if you feel like doing your own language on that level, please go ahead. If possible, we will help you, but you're mostly on your own, but there you go, you might want to do that. It has a monthly release cycle, and if you want to see about what it all does and all the releases, that's where you need to go. The next building block is somewhat opaque. It's called NQP. It's not quite Perl. And it's basically, you could say, the assembly language of Rakudo Perl 6. It is written in NQP. It's self-hosting, which is, I think, quite a feat in itself. But the nice thing about it is that MoarVM is like one backend for NQP. So the only thing that you actually, if you want to have another backend for Rakudo Perl 6, is most of the work that you need to do is actually make it work with NQP. Right? So we have JVM as a backend also at the moment, and there's very extensive work done to make JavaScript backend for Rakudo Perl 6, and we actually can already say hello world in that. It's a start, but all of the other materials like parsing grammars and everything, that all works. So you can use your own, write the programming language in this. We've done this with Perl 6. It also has a monthly release cycle. It actually does not have a website of its own. It's just something that lives in the repo. But yeah, there you go. And it's basically the same for all backends. So basically you need to target NQP if you want to write your own backend. Some people are saying, I want to have an LLVM backend. Well, please go ahead and target NQP. There you go. Rakudo is actually written in NQP and Perl 6. And a tiny bit of C, but you don't really want to know about that. It's very hot code task that we actually done now. And it's basically, I think, about 20 lines of C. The bootstrap is written in NQP. So Perl 6 has all these high-level types like bool and attribute and parameter and subroutine and all that shit. These need to be created, and actually they need to be bootstrapped before you can actually write the grammar that actually parses your Perl 6 code. So that part is written in NQP. It's not nice, because nothing really exists. It is really a bootstrap, but it works. And on top of that, we have the core settings, which is basically giving you all of the even higher level stuff, like sets and bags and all sorts of handy subroutines like map and graph and stuff like that. They're all implemented in Perl 6, and it's part of the settings. And this also has a monthly release cycle, And of course, this is all the same for all backends. Almost. Sometimes the JVM does things slightly differently, so we have some conditional Perl 6 code somewhere in the core settings. So this is for the JVM and this is for everything else, or vice versa. But there used to be a lot more of that, and it used to be way worse when we also had Parrot as a backend. So most of that is gone now, so we don't have to worry about that so much anymore. So what did we do in 2016? Well, we really worked on making 6.c, which is the version of Perl 6 that was released at Christmas, hence the C. Make it faster, and basically make it faster without any incompatible changes to the language, and also make them more reliable and more stable, but mostly make things faster. Yes. So how are we going to make things faster? I'll get back to that later. What are we going to do in 2017? We're actually going to work towards 6D. And this is like, check what the D stands for. Dipalu?
December?
D, it's some kind of Indian fest or something. Yeah, Diwali. Okay, Diwali. Okay, there you go. We're still going to be talking mostly about making things faster. We're actually going to add new features that you actually have to opt in by saying use V6D. And before we have a V6D, we actually have a V6D preview. But you actually can mix precompiled files from 6C and 6D without any problem, because each compilation unit has its own level, and you can actually call code from different levels. So the version of the language is basically depending on the compilation unit, and the precomp doesn't depend on that. So what are the strategies that we have for making things faster? We actually have 7 strategies, not 6. We have static optimizations, we have pre-compilation, we have specialization. This is not a spelling error. We have jitting. We have doing less for the same result. We have better algorithms, and we have manual optimizations. I try to make sense of a lot of the stuff that goes on, but keeping track of all of the developments in all of the systems, in all of the repos is pretty hard. Especially if this is like very about jitting and stuff like that. It's in the Ich bin überfragt category. This is above my pay rate. I am sort of like how I understand cars. I know there's either an electrical or an internal combustion engine in it, and it does stuff. And okay. So all errors and misinformation are completely my fault. But if you really have questions in that area, you should basically go on the ISP channel on Freenode, the 6 channel, or the MoarVM channel if you're really into the MoarVM stuff, and ask questions there. There will be people that can answer you. So, and if you're one of those people here and you see that I'm doing something wrong, please tell me so I can actually fix the slides for next time I make this presentation. So, static optimizations. What it basically does is after your program has been parsed and it has created an internal representation of an abstract syntax tree, it actually goes over the abstract syntax tree and basically finds stuff that it can do. And this abstract syntax tree is a result of both the grammar and the actions. Somebody gave a talk about it this morning about grammar and actions. Anyway, I must have not paid attention. Sorry. But this is basically the oldest type of optimization that we've done in Rakudo. This is basically from way in the beginning, making things faster by looking at the ASTs. Of course, this is very hard work because it's ASTs. It's not something you recognize immediately anymore. So it's basically a lot of stuff. And if you talk about write-only optimizations, this is this is one of those areas. There's only very few people now that actually know what's going on there, and if something breaks there, we have a problem. So we actually try to take things out of the static optimization, basically take it into newer stuff. So it's actually not really in active development anymore. But to give you an example of this, this is an example of doing something 1,000 times in Pro6. What it does, it basically removes the range object. It actually binds the $_ to a native int with the value of -1. Then it turns the 4 into a while loop while pre-incrementing $_ until it hits 1,000. So we have no iterator overhead, we have no unnecessary objects, this is basically really fast. And this actually, this also jits very well into machine code. And this, the empty loop example of this is actually faster than full-file. It's not very useful, but there you go. Another example of static optimizations, and that is still very useful. In Pro6 we have something called multis. So we have a subroutine called foo. We have a prototype for it, proto, which is actually a dispatcher. Now, normally you don't have to actually specify that. I'm just specifying it here so you can actually see that there is such a thing. I have a candidate here that it takes a string, and I have a candidate here that takes an int. And if I call the subroutine in the code later and it sees, hey, 42, that's an int. That's this candidate. Let's just bypass the dispatcher and everything and just basically file a direct call to this subroutine in there. Right, so that's very useful. There you go. So it's still very useful, and actually it also allows compile time error checking, which is very nice because if you call a sub that it doesn't know about it, it will actually find that out during the optimization phase. Because when it looked up in the previous page, if you looked up, you're calling foo here. I don't know any foo. So we can actually tell you that, and basically tell you, well, you called fop here. Oh, I don't know fop. Did you mean pop or foo? So that's very useful. It's a side effect of static optimization, but it's still very useful and still using. Okay, the second thing that we have is pre-compilation. This has always been there from the beginning because it was very clear from the beginning. Sorry, very dry mouth. That grammars would, at least initially, be very slow. And if every time you run a program, you actually need to parse your program, and it's slow, it will actually take a long time to run your program. So we've been pre-compiling for a long time already. So the bytecode of the compilation is actually saved in the file, and it's actually done automatically for you when you need it. And basically it lazily loads the parts of that bytecode when it needs it. So it actually doesn't load the whole thing in once. It basically, you tell it this is where this precomp lives, and then it basically loads it lazily from the file that it needs. This makes it about 500 times as fast as compiling from scratch. How do I know this? Because the core settings are a source file of about 45,000 lines now. And that takes about 45 seconds to parse at the moment. But if you just start up Pro6, it actually loads the pre-compiled version of that. And that takes about a tenth of a second. So that's about the time difference, how faster it is. So we actually use that same process of pre-compilation for the settings itself. Now, pre-compilation is very nice, but it has some conceptual problems. And this is probably going to stay this way, but it has made a lot of people take a hair out of the head for a long time. The problem is that all precompiled code is basically statically linked. But it is dynamically compiled. So if you have 10 different files, they all must know of each other, where they live, and how they are actually put together. So getting the dependency chain introspection working correctly has been really, really hard. And initially we didn't actually have anything like that. So that basically meant every time you compiled a new version of the setting, which was basically really heavy on the people doing core development, because that's what you do all the time, you have to reinstall every single module again that you were using in the ecosystem. I'm so glad we don't have to do that anymore. So you install your module once, you can compile Rakudo as many times as you want, it will just stay installed, and if it sees that it actually needs to recompile it, it will do it automatically for you. Which means that sometimes, after you've done a compilation of Rakudo, it takes a little longer for your program to start. But next time it won't be that. And we're pretty much stable on the computer management. And before, I guess that's one of the small incompatible changes that we had before this Christmas, this last Christmas, was that we really realized that although we always said that loading modules is completely lexical, it wasn't lexical enough. So if you would say module A would use module B, and another module would also use module B, but it would not actually say use module B, it would still work, and it shouldn't. And that's one of the things that we fixed in the release of last month. So we had small breakage, but it was basically just a matter of adding the necessary user command so that everybody knows in this lexical code we're going to use this module, and we have to tell the system that we want that. Why? Because it could be a different version than the one that we're using over there, and they should be able to be installed at the same time and loaded at the same time as well. The next thing is, and there I'm getting into the above my pay rate part, so I'm sort of paraphrasing the documentation here. It's a part of MoarVM since April 2014. If you really want to get into that, this is a very nice blog post that Jonathan wrote about it way back when, and it's still up to date, apart from the things that basically said, well, we will be doing this in the future, and some of them have already been done. It basically at runtime collects information about the bytecode, and basically allows the bytecode optimizations when you actually need them. So it will actually follow what your program is doing and figure out, like, oh, you're doing this 100 times, maybe I can do this faster, right? Which every now and then gives very strange bug reports, like, I have this program and I've run this loop for 157 times. It's okay. 158 times it got boom. Huh? This is a bug in specialization. We've had a few. Most of them are fixed as far as we know, so we haven't had one of those in, I think, at least 6 months now. So specialization. It builds a representation of bytecodes per frame. So basically every block, every subroutine, every frame. It produces a set of cards for a given specialization. So it checks, is this true, is that true, is that true? Then if those all are true, then I can possibly do this. It creates usage counts for dead code elimination. So I'm using this a lot, but not that. Maybe I can throw it away. It actually applies the applicable optimizations. There are not so many at this point, but there are a few, and they are very useful. And then produce the optimized bytecode and run that instead. That's great, but wasn't Perl like a dynamic language? Yes, Perl is a dynamic language. So at any point in time, you can actually create a new role or a new class that inherits or plugs itself in somewhere, and then all of the optimizations basically, well, we don't know about it at the moment. Are they still correct? We don't know. So at every point in time, you should be able to revert every code that we actually optimized to what it was before. This is also pretty tricky, but I think we actually, in the past year, we got most of those problems fixed, and so far so good. Then we have a just-in-time compilation. It basically takes the information from specialization, from fetch, and turns that optimized bytecode into machine code. Right? And then, if possible, if it's like a frame that gets called all the time, it figures out, okay, well, maybe I could just basically replace the call to the subroutine and just insert the code here, and don't worry about all that calling and all that frame shuffling around. So let's do that. But it should still allow for de-optimization. This is very tricky business, and I'm so glad it works almost all the time. And one of the craziest bugs that we found is basically, okay, so it did an optimization here, and then it did JIT there, and then something changed there, and then it had an off by one error but put its stuff back. Stuff like that. The JIT engine itself this is basically the version that we have right now is basically prototype. There's one guy, and he's basically gave a talk here last year, and since then he's actually been studying, and since after that he started working for a big company in Amsterdam, so we haven't seen much of him lately. Yes. But the second generation of this is still under development. He still commits every now and then, so it's not completely stalled, but we all wish that he had some more time. Hi Bart. Doing this a little bit. This is a little nudge. Don't worry about it. Then sometimes we can actually do less for the same result. For instance, one of the problems that we had initially was the whole dependency chain management for precoms, and we start out basically saying, well, you change something, everything needs to be precompiled again. And we've gotten smarter, like, okay, as long as it's the same git hashtag of the core settings, we don't have to do it again. Now we're actually to the point when, okay, we found other ways of figuring out whether we need it or not. So we can actually be pretty smart about that. Another one was actually the sort algorithm that was used, basically uses indexes and basically copied everything first before doing a sort, and then copied everything back. That was one that made sort quite a lot faster. Then another one is don't have to sort 0 and 1 element lists. There's no point setting up stuff when you already know that it's already sorted. And basically try to use natives, but prevent boxing and unboxing from natives to high level objects and low levels. And sometimes you can actually get a better result if you do less. Here's one commit that I have found the past year. This is a method for making sure that a piece of code is the only one between all threads that actually runs at this particular point in time. And it basically should put lock itself, then run the code, save the result, then actually create a leave block to unlock itself, and then return the result. Now, one of the features of a leave block is that it actually gets automatically run at the end when you leave that block. Right? So this is what you need actually. So this whole saving the result is not needed. You just run the code. The leave will take care of it. So, and in the case you don't know, leave is what we call a phaser. And basically, you specify code there that will run whenever a certain condition is met. In this case, leaving this block.
Set on stun.
Sorry?
Set on stun.
Well, yeah, if you want, yeah. The other thing is, of course, making better algorithms. I mean, a lot of the core settings were made under high stress, especially the second part of 2015. There was quite some stress, so the thing was first make it work, then make it faster. So one of the things that were a lot in the core were a lot of get and take solutions. And get and take is really nice if you basically have disconnected gather loop and you have subroutine to takes, and it's very nice because it's all continuation based. But if it's just basically a loop, why are we doing this? So a lot of the things I replaced with iterator based solutions, which are basically much better at splashing and jitting as well, because everything is close together and it makes things are better, easier jitting. So it's easier to spot that we can optimize things. If you have a gather there and a take there, you know there's some continuation going on between the two. Then, of course, we have manual optimizations, and this is basically turn nice Perl 6 code into ugly NQP code. I've been mostly guilty of that, doing that the past year, but yeah, I think if we needed to do something, and this is what I could do. The things that you gain speed and use less memory if you basically go lower level. And the idea is that originally the idea was, okay, we have the core settings. If you want to know how Perl 6 works, you look at the core settings, which is really nice, but I think also a bit naive. Because yeah, if you want to know how you write Perl 5 code, you don't look at the Perl 5 internal file. So having that, sometimes, yeah, I mean the speed differences could be quite significant, like 10, 20 to 30 times faster. In cases like 2,000 times faster, but that was basically somebody was not using their head when they wrote the original code. But using lower level constructs, like this is a very simple example. I have a class that actually has a native int attribute, and it has a method that returns that attribute as a boolean. Now this is perfectly nice Perl 6 code. The question mark means booleanize the value. What it would do, it would actually first upgrade this native int to a high level int, and then call the .bool on it, and then basically return that result. And what I did was basically, there has an NQP op called p6bool, which basically takes a native value and turns it into a Perl 6 boolean. This made it like 3 times as fast. It's a very simple case, and yeah, the readability is sort of acceptable still. There are cases when 3 lines of Perl 6 code were replaced by 80 lines of AQP, but it was like 20 times faster, so people loved it. So, what do we see in speed gain? The spec test is something that we have put to find out how good our system is if we broke something. And in May 2016, it's where I actually started keeping track of that. We did about 1,100 files, about 52,000 tests, and it took 254 ballpark seconds on my machine. Now in February, we have slightly more tests. It took the records that I've seen is 166. So this means that it's about 1.5 times faster for 1.1 time more tests. I must admit I cheated a little bit because between here and there I got a new MacBook Pro. But as you know, the new MacBook Pros of Apple, they're not much faster than the old ones. So this is maybe 10% faster than it was originally, but not more than that. And the thing is that the spec test usually consists of pieces of code that are run once. Does this work? It's not like a lot of loops or stuff. No, does this work? So these are mostly benefits. This time difference is mostly from actually things that happen in MoarVM on that level. Because if I make a single thingy 5 times faster, it's usually just a little thingy somewhere that happens to be used a lot code. But it doesn't really help. And also the code doesn't run long enough for Spash and JIT to kick in. You have one piece of code that you run once, you keep counters, oh, if you do this 100 times, oh, you can get there. So this is just very general. Now, Marijn Brandt, aka Tux, at one point we had a disagreement that he said, I'm going to never write Perl 6 because I hate the syntax and there's certain things that I don't like about it. Some of them got fixed. One of them didn't get fixed, but we actually created a slang for him. So he can actually write Perl 6 in the way that he wants to. It's called slang toxic. But it actually wrote a Perl 6 version of text CSV. And he actually keeps almost daily track of how a particular test from that, and that's the test t-test, which basically just takes a 50,000 line file and runs the module on it, and see how it was doing that. And this is basically the graph from around Christmas to about now. So yeah, it's your average Perl 6 program. It's for some value of average, of course, but it exercises a lot of stuff. It does. It did little grammars. It doesn't do that anymore. That's the only thing that got changed, but I'll get back to that. At Christmas 2015, it took about 14 seconds. We were about here, and but now it's about 5 seconds. Actually, it's less than 5 seconds. So in this past year, we actually made it quite a bit faster. And if you remember that when the first version came out in October 2014. It was at 200 something. So we were 51 times faster than the initial version. It's still 5 seconds. It still makes it, I think, about, if I remember correctly, something like 50 times slower than, no, it's more or less 70 times slower than the Perl 5 version. But the Perl 5 version is actually written in excess. So. So there's one major change that we did to the code in text CSV itself, and that's basically the core of the thing is basically splitting the input and getting the fields. And it used to be a regular expression of basically 4 variables. The thing is that he couldn't actually make those fixed strings because they're actually parameterized. So you can actually say, I want to have a bell signal as the end of line, or something stupid like that. You can also specify that in text CSV. And I actually optimized, or actually implemented a special version of split that takes a number of fixed strings and splits your string according to those strings at the beginning. And that was about 50 times faster than the regular expression version. It is all AQP, it is not nice to look at, but it is very fast. So that made some difference at one point when he started using that. But that's the only thing that actually was changed in the code. So this is basically the only change that we did here. Replace the pipes by commas and make that move the slashes around it, and that was it. So the idea is that test is that it is pure Perl 6 code, that we don't do any optimization there. Sometimes my fingers are really itching getting the NQP in there and making it like at least 20 times faster, but no, we decided I'm not going to touch that. It's pure Perl 6 code like somebody would make it. Now, of course, we have many anecdotal records. A lot of them are in the Perl 6 Facebook group. There's actually a Perl 6 Facebook group, in case you didn't know. And if you made Perl 6 code in the past, when was the last time that you tried it? Try it again and see how fast it goes now. And it's probably going to be a lot faster. So, as I said, 2017, we're going to work on 6D. We're going to actually get the JIT merged. We're going to actually, Larry started working on making grammar parsing faster, which is a very good sign. He's back again, so he's been, I think he's been writing a book or something, but he's been like the past 2 weeks he's been back on the channel again and doing stuff, so that's good. That's a good sign in many ways. And I'll probably be making more manual optimizations. So there you go. This is how we're making Camelia fly faster. Questions?
What's the 100 all about?
Sorry?
What's the 100 about?
Oh, this is actually J.J. Merrilow's thing. I speeded up something, and he actually this is a Unicode symbol for some reason.
What? Okay.
And since we are doing a lot with emojis and Unicode lately in Perl 6, and people love us for it, I understand. I thought it was getting really up to 100 is basically the idea.
Okay.
Eric.
Since Not Quite Perl is written in itself, self-hosting, what is the long-term vision on bootstrapping from source?
The long-term vision is that we should be able to write Perl 6 completely in Perl 6 eventually. But we have other things before we can do that. Well, yes, I agree. Yes, and I'm looking really forward to actually ripping out all the NQP that I wrote the past year and making it Perl 6 again. I would love to do that. I have no emotional bonding with this code. It's it makes things work, but it's ugly.
Is Perl 6 always, is it fundamentally slower than Perl 5 because it's got these different layers?
Yeah. That's
so
basically
even with optimizations and stuff?
Yeah. The thing is, the way I look at it now is that Perl 5 tries to get rid of all of the information that you have in your source code as quickly as possible. Because I don't need it, throw it away. So I want to know the name of the variable in my local electrical variable in my local scope. You can't in Perl 5, as far as I know. You can in Perl 6, because all that information is there. I want to access the plot from my program. You can't in Perl 5. Well, you can read the source file and try to parse it, but right? And all of that stuff is there. All this introspection that we have in Perl 6 that is still around, and that we're going to put to good use at one point, and I guess we're doing this now for maybe 5% of all the possibilities that are in there. But yeah, that's the idea. We have a lot more stuff, and it's not optimized, but we have all of the information there to actually optimize it further. We just need more hands to do it.